Hello there, and welcome to the Sleepy Space Channel. Tonight, the strange and unresolved chapter of our solar system's history, called the Late Heavy Bombardment, the brief, intense storm of impacts that struck every inner world between roughly 4.1 and 3.8 billion years ago, and the moment, almost 4 billion years ago, when that storm was tailing off. The candidate explanations point to a dynamical rearrangement of the giant planets. A wave of scattered small bodies sent inward, the largest basins on the Moon, and Mercury and Mars, all dating to this narrow window. We will visit each of the worlds at the moment when the storm was finally ending, and ask what each of them looked like when the sky began, at last, to grow quiet. If you find these explorations worth your time, a like or a subscribe helps the channel reach others who do. Thank you for being here. But for the next 2 hours, none of this is something you need to carry. Settle in. Let your shoulders soften. Let your breathing slow. Let the day fade away. Let's begin. Part 1. A very old solar system. To begin, picture a date. 3,800 million years ago. A single line drawn across the long history of our solar system. Neither the beginning nor the middle, but a quiet boundary. On one side of it lies the era of formation, the era of fire and impact and rearrangement. On the other side lies the long, comparatively settled Middle Age that holds the worlds we know now. This is the moment we are visiting tonight. 3.8 billion years ago, with the bombardment fading, the giants almost finished, the rocky worlds still being decided. The solar system we know was already in place. The worlds inside it were not yet themselves. The sun overhead is dimmer at this date than the sun we know. Solar models, looking backward across the long, slow brightening of a main sequence star, give the early sun about 70% of its current luminosity. 70% is not a small change. It is the difference between a bright afternoon and a softer one, a different white balance to the day, a cooler equilibrium for any world that depends on the light. The inner worlds compensated for it through their atmospheres. The greenhouse warming of thicker carbon dioxide, of methane, of water vapor, kept them warm enough for liquid water in places we would not expect today. This is the so-called faint young sun condition, and it shines through everything we are about to see. Around the sun, the orbits of the 8 planets are already laid out in their familiar order. Mercury closest, Venus next, then Earth and Mars, and the asteroid belt, then Jupiter and Saturn and the 2 outer giants. The arrangement is recognizable. But the conditions on each world, the surface temperatures, the atmospheres, the oceans or the lack of oceans, the moons that abound and the moons that are still wandering free, all of these were different. The solar system had its skeleton. It did not yet have its faces. We chose this exact date for a reason. 3.8 billion years ago marks the end of a period that astronomers call the Late Heavy Bombardment, a span of roughly 300 million years, during which the inner solar system was repeatedly struck by leftover bodies from the early disk. The largest basins on the face of the Moon, the deepest impact features on Mercury, the oldest scars on Mars, all date to this same narrow window of cosmic time. By the close of the bombardment, the storm of impacts was easing. The inner worlds had received the heaviest of their late deliveries of carbon, water, and metals. The gas giants had finished their largest orbital shuffles. The solar system was beginning its long, quiet Middle Age. Everything on either side of this boundary belongs to a different story. If we were standing somewhere in the solar system at this date, looking up at the sky, we would see almost the same constellations the night sky shows us tonight. the stars do not move quickly enough to have shifted noticeably in only 3.8 billion years. The Milky Way would still arc across the sky in roughly the same band, the same dust lanes, blocking the same starlight from the same galactic center. The familiar outlines of Orion and Sagittarius and Cassiopeia would already be approximately in place, though the patterns we recognize as constellations come from the human eye and would not yet have been named. The deep cosmos overhead was already old. The local solar system inside it was changing rapidly. The inner solar system carried most of that change. The four rocky worlds, Mercury and Venus and Earth and Mars, were each living a different early life. Mercury was being scarred and folded by the last of the bombardment. Venus, perhaps, was warm and wet and not yet lost. Earth was a steam-haloed water world without breathable air, with its moon hanging huge and close in the sky, and the first stirrings of single-cell life beginning in its warm oceans. Mars was wetter than we have ever seen it since, with rivers and lakes and possibly a true northern ocean, but already on the edge of the long, slow loss that would eventually carry its water away. The outer solar system carried less change because the gas and ice giants had no surface for the bombardment to scar. Jupiter and Saturn and Uranus and Neptune absorbed any impacts of the late bombardment without persistent record. Their cloud tops looked then almost the way they look now. Their interiors were warmer, by the same long, slow cooling that any large body undergoes after formation, but their outer appearance was essentially unchanged. The major difference between then and now, for the giants, was their retinues of moons. Several of their large companions were already in place, formed from the circumplanetary disks of their parent worlds in the first few million years. But others, including the largest moon of Neptune, were still drifting somewhere out in the cold and the dark, waiting to be captured. In the inner and outer worlds, the asteroid belt was thinning. The nice model rearrangement of the outer giants, the slow migration of Jupiter and Saturn and Uranus and Neptune to their final orbits, had crossed a resonance and scattered a great wave of small bodies. Some struck the inner planets and produced the bombardment. Some were ejected to interstellar space. Some were flung outward and seeded the Oort cloud, the great spherical shell of long-period comets, at distances of thousands to 100,000 astronomical units, where they still sit today. The Kuiper belt, that flat, sparse ring of icy bodies just beyond Neptune, was being structured by Neptune's outward push, and Pluto and the other large dwarf planets were settling into their modern orbits, including the resonant orbit that locks Pluto in step with Neptune and keeps the two from ever meeting. At this moment, this single date 3.8 billion years ago, almost everything about our solar system was either just settled or just about to be decided. The 8 planets were in place. The faint young sun shone over them all. The bombardment was tailing off. The worlds were still strangers to themselves. Tonight, we walk slowly through each of them in turn and ask what they were like at this moment. The answers are not what most of us imagine. Habitability, at this date, was the rule, not the exception. 3 rocky worlds had water. 2 would lose it. It may help to consider how this date sits inside the longer history. The solar system itself is now about 4.6 billion years old. We are visiting it tonight at roughly 17% of the way into its current life, just past the dramatic early chapters and just before the long, quiet middle. If the entire history of the solar system were compressed into a single 24-hour day, 3.8 billion years ago would be about 4 hours after midnight. The Sun has been on the main sequence for the equivalent of about 2.5 of those hours. The solar system is no longer brand new at this date. It is past its earliest violence. But it is not yet what it will become. The light from the dim young sun reaches the inner worlds in the same 8 minutes or so that it takes today, since the speed of light has not changed and the orbits are nearly the same. The outer worlds receive their light hours later. The light from a young sun, weaker but not differently colored, plays across the same arrangement of bodies that will, 3.8 billion years later, contain everyone who will ever wonder what their solar system looked like at this moment. The arrangement at this date is the long memory of the solar system we live in tonight. Almost everything we will see in this video is, in some sense, what is buried under everything that has happened since. Part 2. The Late Heavy Bombardment. The Late Heavy Bombardment is the name given to a period between roughly 4.1 and 3.8 billion years ago, during which the inner solar system was struck by leftover bodies from the early disk at a rate far higher than the steady cratering rate we see today. It is one of the most important events in the history of our worlds, and the evidence for it is written across every solid surface we have studied closely. The clearest record of the bombardment is on the face of the Moon. The largest dark patches we see when we look up at a full moon, the Maria, are the lava-filled floors of the largest impact basins. Imbrium, Serenitatis, Chrysium, Nectaris, all of these are basins more than 1,000 kilometers across, gouged out by single enormous strikes. When samples of lunar rock from the basin rims were dated, almost all of the largest basins clustered in the same narrow window of time. They were not formed steadily across the Moon's history. They were formed in a brief, intense pulse between 4.1 and 3.8 billion years ago. The same clustering shows up on Mercury. Caloris Basin, the great impact feature near one of Mercury's 2 hot poles, dates to this same window. So does much of the heavily cratered terrain of southern Mars. So do the oldest features on any of the moons that have preserved their early surfaces. Across the inner solar system, a single brief storm of impacts laid down basins and scars on every world that had a surface to be scarred. After that storm, the rate of impacts dropped sharply to roughly its modern level. The solar system, in the language of geologists, calmed down. The leading explanation for why this happened is the Nice model, named for the city in France where it was developed. The argument is dynamical. After their formation, the 4 giant planets did not orbit at exactly the distances they orbit now. Jupiter and Saturn, in particular, started slightly closer together than they sit today. As the disk of gas dispersed, and as the residual small bodies of the early solar system gravitationally tugged on the giants slowly migrated. At some point, Jupiter and Saturn crossed a mean motion resonance, where Saturn made 1 orbit for every 2 of Jupiter's. The crossing of that resonance pumped energy into the orbits of the other giants and sent the whole system briefly into chaos. The chaos lasted, in cosmic terms, only a brief time. Uranus and Neptune were thrown outward by gravitational interaction with the gas giants. The wave of energy reached into the regions where the leftover planetesimals of the early solar system still drifted and scattered them in every direction. Some were thrown inward and struck the inner planets. Some were thrown outward and seeded the Oort cloud. Some struck the giants themselves. The rate of impacts on every solid world inside Jupiter's orbit spiked. That spike, lasting roughly 300 million years, is the Late Heavy Bombardment. By 3.8 billion years ago, the rearrangement was complete. The giants had reached approximately their current orbits. The supply of leftover planetesimals in the inner solar system had been largely exhausted, either absorbed by collisions or ejected to faraway orbits. the cratering rate began to drop steeply. The bombardment was ending. The solar system was settling. The bombardment is not only a story of destruction. It was, in important respects, a story of delivery as well. The bodies that struck the inner worlds carried water, carbon, nitrogen, and the basic building blocks of biochemistry. Earth's oceans almost certainly contain a meaningful contribution from this late delivery. The same is likely true for the early oceans of Venus and Mars, if those oceans existed. The same icy and carbonaceous bodies that gouged out craters on Mercury and the Moon also added the volatiles that would, on the right-sized worlds at the right distances, become atmospheres and oceans, and eventually life. The single most studied late impact in modern times offers a glimpse of what the bombardment looked like in miniature. In the early 1990s, a comet broke apart into more than 20 fragments and struck Jupiter in a chain of impacts over several days. Each fragment, although small by solar system standards, released energy comparable to the largest nuclear explosions humans have ever built, and each left a dark scar in Jupiter's cloud tops that was visible for weeks. The fragments sank into the deep atmosphere and vanished. By the end of the year, the scars had faded. Jupiter, the largest and quietest of the giants, had absorbed and forgotten its bombardment. The inner worlds could not forget so easily. Each strike, on a rocky world without a deep cloud deck to swallow it, left a permanent record. Each crater, above a certain size, produced extensive ejecta blankets, scattering hot material across vast distances. The largest strikes produced basin-wide melt sheets and seismic energy strong enough to focus on the planet's opposite side and produce chaotic terrain there. The bombardment did not merely scar the surfaces of the inner worlds. It heated them, melted them, mixed their compositions, and reset their geological histories. At 3.8 billion years ago, this was the moment when the storm was tailing off. Each of the rocky worlds was still bearing fresh wounds. The lava in the floor of Caloris Basin on Mercury was still cooling. The Maria of the Moon were either freshly filling or about to. The river valleys of Mars had not yet had time to settle into their final patterns. Earth had taken its own share of strikes, though plate tectonics and weathering have since erased almost all the evidence. The bombardment had touched every inner world, and it was, finally, ending. Part 3. The Giants. Already themselves, the gas and ice giants, those 4 large outer worlds beyond the asteroid belt, are remarkable for how little they changed across the past 3.8 billion years. The rocky planets we will visit later in this tour will look almost unrecognizable in their early forms. The giants will look almost the same. The reason is structural. A gas giant has no surface for an impactor to scar. A comet or asteroid that strikes Jupiter or Saturn sinks into the cloud deck like a stone into deep water. The energy is absorbed. The visible record vanishes within months. The giant moves on. Begin with Jupiter. At 3.8 billion years ago, Jupiter is already the largest world in the solar system. Its mass, its layered interior structure, its rapidly rotating banded cloud system, all of this is already in place. Below the visible cloud tops lies an envelope of molecular hydrogen, hundreds of kilometers thick. Below that lies a mantle of metallic hydrogen, compressed by the planet's own enormous weight into a state where hydrogen behaves like a liquid metal, conducting electricity, generating the most powerful planetary magnetic field in the solar system. At the center lies a small, fuzzy core of heavier elements, perhaps not as sharply defined as we once thought, more mixed into the surrounding metallic hydrogen than a clean, rocky kernel. Jupiter at this date has all of this. What it does not yet certainly have is its most famous feature. The Great Red Spot, the enormous southern anticyclonic storm that has been observed continuously for at least the past 400 years, may or may not be present 3.8 billion years ago. The age of the Great Red Spot is contested. Some lines of evidence suggest it has been turning for tens of thousands of years. Other lines suggest it may have replaced an earlier, similar storm only relatively recently. We cannot say with confidence whether a long-lived southern red oval is part of Jupiter's appearance at this date. We can say that the banded structure of zones and belts, the brown and cream and white horizontal stripes, is essentially the same as today's. Jupiter has its 4 largest moons, the Galilean moons, already in place. Io, Europa, Ganymede, and Callisto formed from Jupiter's own circumplanetary disk in the first few million years after the planet itself. By 3.8 billion years ago, they have settled into their modern orbits and into the resonant relationship that locks the inner 3 together. Io was already volcanic, although its surface looks different from today's, its sulfur eruptions producing different colored deposits. Europa already has an icy shell over a liquid water ocean, though the ice may be thicker at this date because the sun is dimmer. Ganymede, the largest moon in the solar system, is already differentiated, with an icy crust over a rocky interior. Callisto, the outermost of the 4, is already heavily cratered, although its modern surface has the additional history of every late impact since. What Jupiter does not yet have is its full retinue of irregular outer moons. Many of those small bodies, captured Trojans and captured Kuiper Belt members, were not yet bound to Jupiter at 3.8 billion years ago. They would be added piecemeal across the next several billion years, snared one at a time by close passes through Jupiter's vast gravitational well. The Jupiter system of 3.8 billion years ago is a tidier system. 4 big moons in orderly orbits, a few smaller inner companions, and the rest of the local space still empty. Saturn at this date is similarly almost identical to today's Saturn in appearance. The same pale gold and cream banding of cloud tops. The same hexagonal jet at the North Pole, since that feature comes from the planet's atmospheric dynamics rather than from any short-lived storm. The same slow rotation. The same hydrogen-helium structure, with helium rain falling slowly through the deep envelope. Saturn, at 3.8 billion years ago, seen from a distance, would have been a paler world, wearing the same family resemblance to its modern self. The largest difference for Saturn is the rings. Multiple independent lines of evidence point to the main ring system being much younger than the planet itself. The rings are too bright. They contain too little dust contamination. They lose mass too quickly through ring rain, the slow drizzle of ring material into Saturn's atmosphere. Run these processes backward, across geological time, and the main rings appear to be perhaps a few 100 million years old, possibly younger. If that estimate is right, Saturn, at 3.8 billion years ago, was either ringless or wearing a faint precursor of rings, possibly the remnants of an earlier disrupted moon. The Saturn we recognize, that crowned figure with the bright bands of ice, may be a relatively recent face of the planet. The Saturn of 3.8 billion years ago turned in the cold and the dark with bare shoulders. It still had its moons. Triton, the largest, was already orbiting Saturn at this date with its thick nitrogen atmosphere and its slow circulation of methane. Enceladus, much smaller, was already in its orbit, and almost certainly already losing some of its interior heat through tidal flexing in a slightly eccentric path. Whether Enceladus had its modern subsurface ocean at 3.8 billion years ago is uncertain. The tidal warming that sustains it may have been steadier in the deeper past, when other moons in the system kept Enceladus on a more eccentric orbit. But the geological evidence for early plumes is not preserved. We can say with reasonable confidence that Enceladus was warming. Whether it had broken through to a stable internal ocean is open. Uranus, the first of the two ice giants, was already tilted on its side at this date. The catastrophic giant impact that knocked Uranus's rotation axis nearly perpendicular to the ecliptic happened in the planet's first few 100 million years. By 3.8 billion years ago, Uranus had been turning on its side for a very long time and would continue turning on its side forever after. Its appearance was the same pale blue-green of methane-tinted cloud tops, the same bland and featureless face it shows us tonight. Its interior was the ice giant interior, a thick mantle of supercritical water, methane, and ammonia under high pressure, surrounding a small rocky core. Neptune, the outermost giant, was nearly identical to its modern self in structure, atmospheric chemistry, and the cold, deep blue of its cloud tops. Its supersonic equatorial winds, the strongest sustained winds on any planet in the solar system, were probably already underway. Its great dark spots, those transient anticyclonic storms that form and fade across decades, were almost certainly forming and fading at this date as well. What Neptune did not yet have was its largest moon. Triton, today the most prominent of Neptune's companions, was not yet part of the Neptune system at 3.8 billion years ago. We will come to that capture later in our tour. Part 4. Mercury, the scarred memory. Mercury, at 3.8 billion years ago, is, in a sense, the freshly scarred witness of the late bombardment. Closest to the Sun, smallest of the recognized planets, dense and iron-cored, it bore the heaviest cratering per square kilometer of any of the inner worlds. Without an atmosphere thick enough to slow incoming bodies, every impact reached the ground at full speed. Without weather to erode the craters or plate tectonics to fold them away, every strike left a mark that, in the bombardment era, was still being kept. The physical body of Mercury at this date is broadly the same as the body we map today. It is small, only slightly larger than the Moon. Its iron core is large in proportion to the rest of the planet, perhaps 3/4 of its radius. Above the core lies a thin silicate mantle and an even thinner silicate crust. There is essentially no atmosphere, only an exosphere so thin that its constituent atoms travel from one point on the surface to another without colliding. The exosphere is constantly resupplied by hydrogen and helium captured from the solar wind, by sodium and potassium liberated from the surface by micrometeorite impacts, and lost again to space. The surface at 3.8 billion years ago is divided between two distinct terrains. The first is the heavily cratered highlands, which are saturated with impact craters. Saturated, in the language of planetary scientists, means that the surface has been struck so many times that every new crater overlaps and partially erases an older one. The highlands are the patient archive of the bombardment, a surface where every visible square kilometer has been hit by something at some time. The second terrain is the smooth plains, which are large volcanic floods of low-viscosity lava that have buried earlier cratered terrain. The smooth plains are still young at this date. Some are still being filled in as fissures open and basaltic lava continues to flow. The largest single feature on Mercury, then and now, is Caloris Basin. Caloris is a vast impact crater on Mercury's leading face, about 1,550 kilometers across, formed by the strike of an enormous body during the bombardment. At 3.8 billion years ago, the floor of Caloris is still warm. Lava is still seeping up through cracks in its base. The basin is a young scar. Across the planet from Caloris, exactly antipodal to the impact site, there is a region of chaotic terrain, a hilly, fractured surface produced by the focusing of seismic waves from the impact. The energy of the strike traveled through Mercury's interior, converged on the opposite face of the planet, and shook that surface so violently that it broke up the existing terrain into a jumble of hills and depressions. The Caloris and its antipode is one of the most striking impact and aftermath signatures preserved on any rocky world. Mercury, at 3.8 billion years ago, is also volcanically active, in a way it is not today. Its iron-rich interior is still warm enough to drive basaltic eruptions, and lava continues to flow through fractures, flooding lowlands and burying older craters. This is the period that produces the smooth volcanic plains visible today. By a billion years later, this activity has largely ended. At 3.8 billion years ago, it is still going. As Mercury's core continues to cool, the entire planet contracts. Its surface area shrinks. The shrinkage produces compression folds, long curving cliffs called lobate scarps, where one slab of crust has been thrust over another. These scarps are still propagating across Mercury today, very slowly, but at 3.8 billion years ago, they were younger and more freshly cut. Many of them cross older craters, which tells us they postdate the heaviest bombardment. They fold the bombardment's record into themselves, lifting the floor of one ancient crater up over the rim of another, telling a layered story. The temperatures on Mercury, then, are essentially the temperatures on Mercury now, given that the surface temperature on a body with no atmosphere is set by the balance between solar input and radiative output, and the geometry has not changed. The day side of Mercury, when the sun is overhead at perihelion, reaches temperatures hot enough to melt lead. The night side, with no atmosphere to retain the day's heat, cools to deep cold. The youngest craters at this date still have central peaks, sharp rims, and visible ejecta blankets. The oldest craters are already eroded down by thermal cycling, by the slow expansion and contraction of rocks across temperature swings that would shatter terrestrial cliffs. The orbit of Mercury at 3.8 billion years ago is already in its modern 3:2 spin-orbit resonance. The planet rotates 3 times on its axis for every 2 orbits it makes around the Sun. This resonance was established early, locked in by tidal forces, and is one of the planet's most distinctive dynamical features. The tidal coupling to the Sun is strong, far stronger than the tidal coupling between Earth and the Moon. The Sun raises tidal bulges in Mercury's iron-rich body of immeasurable size, flexing the planet on every orbit. That tidal flexing contributes to internal heating, although the main source of heat is still the slow cooling of the iron core. For an observer standing on Mercury at this date, the sky would have held a sun roughly twice as wide as it appears from Earth. The light would have been cold and unfiltered. There is no atmosphere to scatter blue or to soften shadows. The horizon, close because of Mercury's small radius, would have curved sharply. The ground would have been warm in some places, freshly molten in others. The shadow of any standing object would have been knife-edged, the contrast between sunlit and shadowed surface enormous. Mercury, then and now, is one of the most extreme worlds in the solar system. At 3.8 billion years ago, it was simply newer in its extremes, still bearing the freshest of its long catalogue of wounds. The polar regions of Mercury at 3.8 billion years ago deserve a quiet aside. Because of Mercury's extremely small axial tilt, the floors of deep polar craters never receive direct sunlight. Some of those permanently shadowed floors are cold enough to trap volatile material indefinitely. The polar deposits we see on modern Mercury, mixtures of water, ice, and organic compounds delivered by cometary impacts, were already accumulating at 3.8 billion years ago. Every cometary strike at high latitudes added a small contribution to the cold trap. The deposits have been building for billions of years. The water locked at Mercury's poles tonight is partly water that arrived during the bombardment era. The same scattered comets that delivered water to Earth and Venus and Mars also added their small contribution to Mercury, and the polar cold traps kept it. The interior of Mercury, at 3.8 billion years ago, was still settling into the planet's modern configuration. The iron core, which makes up an unusually large fraction of Mercury's total volume, was still releasing formation heat. The mantle convection above the core was driving the volcanism we have already described. The thin silicate crust was being deformed by the ongoing contraction. None of these processes happened all at once. They each had their own slow timescale, and at 3.8 billion years ago, they were all running at their early elevated rates. One additional puzzle about Mercury is worth a brief mention. The reason Mercury has such a disproportionately large iron core is debated. The leading explanation is that early Mercury, before the bombardment era, the bare core was largely preserved. A thin silicate mantle and crust were rebuilt over the subsequent hundreds of millions of years from the remaining material. If this picture is correct, then Mercury at 3.8 billion years ago was the rebuilt aftermath of an even earlier catastrophic event. The planet had already been remade once before the bombardment finished it off. Mercury's relationship with the Sun at this date was also more complicated than the simple orbital geometry suggests. The Sun's enhanced ultraviolet output and the stronger solar wind at 3.8 billion years ago meant that Mercury's exosphere, the thin envelope of atoms barely held to the surface, was being constantly stripped and replenished at a faster rate than today. Sodium and potassium atoms, ejected from the surface by particle impacts, formed a tenuous tail behind the planet, blown back by the solar wind in the direction away from the Sun. That tail, an early version of the comet-like exospheric tail that we observe on Mercury today, would have been more pronounced under the more active young Sun. From a distance, Mercury at 3.8 billion years ago would have looked something like a small bare body with a faint glow trailing behind it, the residue of its surface being slowly carried away by the wind from the star it orbited. Finally, the day length on Mercury at 3.8 billion years ago, measured against the Sun rather than against the stars, was the same long solar day it has today. Mercury's 3:2 spin-orbit resonance means that one solar day on Mercury, the time from one noon to the next, takes 2 Mercurian years, about 176 Earth days. The planet has the longest solar day of any body in the solar system. At 3.8 billion years ago, that long solar day was already locked in by tidal forces. The cycle of extreme heating and extreme cooling, running on a 176-day rhythm, was already established. Every point on the surface received its long stretch of sunlight, followed by its long stretch of dark, in the same rhythm we measure today. Part 5. Venus, the world that might have been. Venus today is the hottest world in the solar system. Its surface temperature averages about 460 Celsius, hotter than Mercury's dayside, hot enough to melt lead. Its atmosphere is 90 times the surface pressure of Earth's atmosphere, dominated by carbon dioxide, and its high clouds are made of droplets of concentrated sulfuric acid. Standing on the surface of modern Venus would be like standing in a furnace under the weight of a kilometer of water, breathing nothing breathable while caustic rain that never reaches the ground evaporates back into the high atmosphere overhead. This is not what Venus looked like 3.8 billion years ago. The single most important fact about early Venus is that it may not yet have been Venus. The hellish modern surface, with its carbon dioxide ocean of an atmosphere and its high acid clouds, was not the planet's original condition. Climate models of early Venus, calibrated against the faint young sun, find that the planet could have hosted standing liquid water at the surface for hundreds of millions of years, possibly for as long as 2 to 3 billion years before the runaway greenhouse finally closed. The Venus of 3.8 billion years ago is, on the most current understanding, a world inside that long habitable window. A world that had not yet become what we see now. Consider the basic conditions. Venus and Earth formed at nearly the same time, in nearly the same region of the inner disk. They are nearly the same size and mass, with Venus slightly smaller. Their basic chemical building blocks are similar. The main difference is their distance from the Sun, with Venus about 70% of Earth's distance. Today, that closer distance keeps Venus much hotter. But 3.8 billion years ago, the Sun was about 70% as bright. The warmer-than-Earth orbit of Venus, multiplied by the dimmer-than-today Sun, gives a thermal environment in which surface liquid water becomes plausible. Three-dimensional climate models of early Venus, given a slow rotation and a modest atmosphere, produce stable surface temperatures of perhaps 50 Celsius. Warm by our standards, but well within the range that allows oceans. The likely picture at 3.8 billion years ago is of Venus, with shallow seas, drifting cloud decks, possibly continents, possibly weather patterns we would recognize. A blue-green or pale yellow world, partly hidden under clouds. The water itself was delivered, in part, the way it was delivered to Earth. By impacts of icy and carbonaceous bodies during and after the bombardment. Cometary and asteroidal contributions added water, carbon, nitrogen, and the salts that would dissolve into early oceans. The atmosphere at 3.8 billion years ago would have been carbon dioxide dominant by modern standards, but considerably thinner than today's runaway atmosphere, with substantial nitrogen and water vapor. The interior of Venus at this date was similar to its modern interior. A silicate mantle around an iron-rich core. Whether Venus then had plate tectonics, as Earth does, is contested. Earth uses water-loaded mantle convection to keep its plates moving. If early Venus had abundant water in its mantle, it may have had at least episodic plate-like behavior at this date. Whether or not Venus had a magnetic field at this date is also uncertain. Today, Venus has essentially no global magnetic field. Earth maintains its field through a dynamo in its molten iron outer core, and that dynamo requires a particular combination of core temperature, composition, and convection. Venus, despite being nearly Earth's twin in size, has lost its dynamo or never strongly had one. At 3.8 billion years ago, with a wetter interior and possibly more dynamo activity, it may have had a weak one. The surface itself at this date was almost certainly volcanic. Long basalt plains, broad shield volcanoes, ridged regions of compression and extension. Above this, when the sky was clear, there would have been a young sun's pale light and weather patterns shaped by a slowly spinning world. When the sky was cloudy, the atmosphere would have rained. Actual liquid water rain, falling onto warm basalt and pooling in low places. The rain would have weathered the volcanic rocks, dissolving carbon dioxide from the air into carbonic acid, which would have reacted with the basalt to lock up some of the atmospheric carbon dioxide into solid carbonate minerals. This is the same process that, on Earth, slowly removes carbon dioxide from the atmosphere over geological time. On early Venus, the same process may have been buying time against the runaway greenhouse. The light reaching the surface, when it broke through the clouds, would have been softer and a little more orange than the sun we know. The pale water of shallow seas would have caught that light. Tides would have been gentle because Venus has no large moon to raise them. Wind patterns would have been slow because Venus turns slowly. The whole world would have felt patient, in a way the modern Venus does not feel patient. Venus did not stay this way. The runaway greenhouse, the process by which evaporating water vapor adds to atmospheric greenhouse warming, which evaporates more water, which adds more warming, eventually overwhelmed the surface ocean. Water vapor rose into the upper atmosphere, where ultraviolet light from the sun broke it apart into hydrogen and oxygen. The hydrogen, light enough to escape Venus's gravity, drifted away to space. The oxygen reacted with surface rocks and was sequestered. The carbon dioxide that had been chemically locked into surface carbonate rocks was outgassed back into the atmosphere by volcanism, without enough rain to wash it back down. The greenhouse closed. The atmosphere thickened. The temperature rose. By perhaps 1 billion years ago, Venus had become the world we see now. The transition took hundreds of millions of years. Crucially, 3.8 billion years ago, that long collapse was still in front of Venus. The world we are visiting in this part is the version that had not yet lost its oceans. The version where the question of whether Earth-like surface conditions could survive close to a star was still being answered, not yet decided. For an observer standing on early Venus at this date, near a low coast, the sun setting paler than Earth's, the clouds banded in slow daylight colors, a long, shallow ocean catching the light. No grass, no trees, no birds. Only the slow tide of a quiet world, and the question, still open, of whether anything alive had begun to drift in those waters. The atmospheric composition of early Venus, if it is right that the world had reduced surface water and a modest carbon dioxide atmosphere, would have been chemically interesting in the way Earth's atmosphere has been chemically interesting. The right ingredients were present. The right energy sources were present. Whether biology took hold there, even briefly, is a question that the patient probing of future missions may someday be able to answer. The day on Venus. Modern Venus rotates very slowly, with a single day on Venus, measured against the stars, taking about 243 Earth days, longer than the Venusian year. Modern Venus also rotates in the retrograde direction, opposite the rotation of most other planets. How early Venus rotated is uncertain. Some models suggest the planet may have rotated more rapidly in the past and was slowed by atmospheric tides as its dense modern atmosphere developed. Other models suggest that Venus has always rotated slowly. Whatever the early rotation rate, the long Venusian day at 3.8 billion years ago, however long it was, would have meant slow weather patterns and gradual temperature changes between day and night. Another feature of early Venus is the question of plate tectonics. Earth's plate tectonics is driven by the convection of a mantle that has just enough water dissolved in it to keep the rocks soft and ductile. Early Venus, if it had abundant surface water and a wet mantle, may have had at least episodic plate-like behavior. Some of the geological features of modern Venus, including the deformation belts called tesserae, may be remnants of this early tectonic activity. The tesserae are among the oldest surface features on modern Venus, dating to a time when the surface was deformed in ways that may have involved plate-like motions. At 3.8 billion years ago, the tesserae we see today were either being formed or had recently formed, and the planet's tectonic regime may have been more Earth-like than it is now. A third feature is the loss process itself. As Venus's atmosphere thickened across the next 2 billion years, the greenhouse warming accelerated and the surface water began to evaporate. Water vapor rose into the upper atmosphere. There, ultraviolet light from the active young sun broke water molecules apart into hydrogen and oxygen. The hydrogen, being the lightest gas, escaped Venus's gravity over time, drifting away into interplanetary space. The oxygen, heavier and more chemically reactive, was largely absorbed by surface rocks, oxidizing the basaltic crust. Across hundreds of millions of years, this asymmetric loss removed water from Venus in a one-way process. The water that was lost did not return. The planet's water inventory was being slowly drained, even as its carbon dioxide inventory was being added to by ongoing volcanism without the rain-driven weathering that would normally remove it. The runaway became inevitable, not because of any single event, but because of the slow accumulation of small imbalances over geological time. A fourth feature is the temperature gradient between equator and poles. On modern Venus, the surface temperature is nearly uniform from equator to poles because the dense atmosphere transports heat efficiently across the planet. On early Venus, with a thinner atmosphere, the temperature gradient may have been greater. The equator may have been warmer than the poles, allowing for the possibility of polar ice or polar oceans, even when the equatorial regions were ice-free. Whether early Venus had any polar ice is unknown. The geological record on the modern surface has been heavily reworked by subsequent volcanism, erasing any direct evidence. Part 6. Earth, the strange cradle. Of all the worlds we are visiting tonight, Earth, at 3.8 billion years ago, is perhaps the most unfamiliar. It is the world that, of all of them, has changed the most. It had a core, a mantle, a crust, a global ocean. It did not have free oxygen. It did not have continents in the modern sense. It did not have multicellular life, or land plants, or animals, or anything we would recognize from a modern landscape. The day was shorter, perhaps as short as 6 hours. The moon hung in the sky much closer and much larger than we have ever seen it. The atmosphere was a different sky, orange and grey and warm, and the rains were warm rains under a dim, slightly orange sun. 3,800 million years ago is the boundary between the Hadean and the Archean eons of Earth's history, specifically the very early part of the Eo-Archean. The Hadean, named for the underworld, ran from Earth's formation about 4.6 billion years ago through about 4 billion years ago. It was the era of the magma ocean phase, the moon-forming impact, the first cooling, the first crust. By 3.8 billion years ago, much of that initial chaos was behind Earth, though the late bombardment was still tailing off. The planet had a solid crust. It had oceans of liquid water. It had the first known sedimentary rocks, the oldest dated metasediments having formed around this time and survived, preserved in greenstone belts in Greenland, and a handful of other ancient cratons. The crust at this date was thinner than today's continental crust. The interior was hotter beneath it, perhaps 200 Celsius hotter than today's mantle. The mantle convected vigorously, driven by heat from formation, by the decay of short-lived radioisotopes, and by the continuing tail of impacts. Whether plate tectonics was operating in its modern form at 3.8 billion years ago is contested. Some lines of evidence point to a different regime, with smaller and faster-moving microplates, or perhaps a stagnant lid broken only intermittently by mantle plumes. Other lines suggest the basic machinery of plate tectonics was already underway. What is clearer is that the rate of crustal recycling, the speed at which new oceanic crust was created at ridges, and old crust was returned to the mantle at subduction zones was much higher than today. Volcanic island arcs, hot mantle plumes, and frequent eruptions kept the surface geologically restless. Earthquakes were continuous. Hydrothermal vents on the ocean floor were active everywhere, pumping out hot, mineral-rich water that drove the chemistry of the early ocean. The ocean itself was warm. Some estimates put the average sea surface temperature at 3.8 billion years ago, somewhere between 50 and 80 Celsius, comparable to a hot bath in places. The water was salty, but with a different dissolved chemistry than today's. Iron dissolved freely in seawater because there was no free oxygen to oxidize it. The seas would have looked greenish or yellow-brown, the way modern iron-rich waters do. Hydrothermal vent fluids, rich in hydrogen sulfide, mixed into the warm seas around volcanic ridges. The mineralogy of the early ocean is preserved in some of the oldest banded iron formations, where alternating layers of iron oxide and silica record cycles of iron precipitation that depended on the chemistry of an oxygen-poor sea. The sky overhead was thick with carbon dioxide, methane, water vapor, and nitrogen. The carbon dioxide and methane carried the greenhouse warming that kept the surface above freezing despite the faint young sun. Without that greenhouse, the early Earth would have been globally frozen. The carbon dioxide levels were perhaps tens of times higher than today's. Methane was a non-trivial component, possibly produced both by abiotic processes and, later, by the earliest methanogenic microbes. The air would have appeared faintly orange or pinkish to a modern eye, with hazes of organic aerosols periodically forming in the upper atmosphere. There was no ozone layer because there was no oxygen. The surface received unfiltered ultraviolet radiation. Any life that existed had to live underwater or under rock to survive it. There were no large continents in the modern sense. The first stable cratons, the cores of today's continents, were just beginning to form. Most of the surface was ocean. Small volcanic islands and proto-continental fragments rose above the waterline, and these would have looked like clusters of dark, freshly cooled basalt platforms with white surf and warm springs around their edges. Most of these early proto-continents were small, short-lived, repeatedly remelted, recycled into the mantle, and reborn. By the late Archean, the continental crust would begin to grow significantly in volume. By 3.8 billion years ago, that growth was just beginning. The Moon at 3.8 billion years ago was substantially closer to Earth than it is today, perhaps 2/3 of its current distance. It would have appeared much larger in the sky, half again as wide or perhaps more. Its gravitational pull on the oceans was correspondingly stronger, producing tides of staggering height that swept hundreds of kilometers across the warm, low coastlines. The day, slowed continuously by tidal friction with the Moon, was much shorter than today's. Estimates range from about 6 hours to about 10 hours. Nights were short and bright. The full moon would have flooded the world in cool light. The oldest secure evidence of life on Earth is approximately this old. The first stromatolites, layered mats of microbial colonies that trap and bind sediment, appear in the geological record beginning around 3.7 billion years ago, and there are isotopic hints of biological carbon fractionation even earlier. By 3.8 billion years ago, microbial life was either just establishing itself or had been present for a few 100 million years already. These earliest organisms were simple prokaryotes. They were anaerobic, chemosynthetic in many cases, harvesting energy from hydrothermal vents, from sunlight, in the form of early non-oxygen-producing photosynthesis, and from the chemical disequilibrium of a planet still settling. They consumed carbon dioxide. They produced methane and eventually oxygen, but the oxygenation of the atmosphere was hundreds of millions of years still ahead at this date. A modern human dropped on the shore of early Earth at 3.8 billion years ago would have died quickly. The air would have been unbreathable. The ultraviolet would have burned exposed skin in minutes. The tides would have swept anyone away from low coasts. And yet, under it all, there was salt water and gentle warmth and the beginning of life. It was the cradle, not the home. There are a few other features of Earth at this date that deserve quiet attention. The first is the way the ocean chemistry tied itself to the atmospheric chemistry. With no free oxygen in either the ocean or the air, iron and other reduced metals could remain in solution at high concentrations. The ocean held dissolved iron at perhaps 100 to 1,000 times the concentration of modern seawater. When that iron eventually began to precipitate out, hundreds of millions of years later, it would form the banded iron formations that today supply much of the world's iron ore. The reservoir was being filled at this date. The precipitation would come later, with the rise of oxygen. A second feature is the role of the oldest known rocks. The oldest dated minerals on Earth are zircon crystals from the Jack Hills region of Western Australia, with ages running back to about 4.4 billion years ago. Those zircons are older than the rocks they are now embedded in, having been eroded out of even older rocks that have not survived. The chemistry of the zircons tells us that liquid water was probably present on Earth's surface from very early on, possibly within a few 100 million years of the planet's formation, far earlier than the 3.8 billion years ago date we are visiting tonight. By the time we arrive, water has been here for hundreds of millions of years already. A third feature is the location of the first sedimentary rocks. The oldest preserved sedimentary rocks are from the Isua Greenstone Belt in southwestern Greenland, from approximately this date. They contain layered chemical sediments, including banded iron formations and chemical limestones that record the conditions of the ocean and the atmosphere in which they formed. The Isua rocks are the closest thing we have to a direct sample of the Earth of 3.8 billion years ago. They tell us that water was present, that the atmosphere was oxygen-poor, and that the chemistry of the ocean was already complex enough to record itself in layered minerals on the sea floor. A fourth feature is the absence of land in any familiar sense. There were no plants on land because there were no plants. There were no soils because soil formation requires biology. The land surfaces of the small proto-continents and volcanic islands were bare basalt and weathered rock, scoured by wind, with no roots to hold sediment in place. Rainwater on the bare basalt picked up dissolved silicates and carbonates and carried them into the ocean, where they slowly built up the chemistry of the early sea. The water cycle was running, but with a different terrestrial half. The runoff was faster and more concentrated. The chemistry of the seas was being shaped by the chemistry of weathering on uninhabited basalt. A fifth feature, finally, is the chemistry of life itself. The first organisms had to manage the same fundamental problems that biology has always managed. How to harvest energy. How to maintain a chemical gradient across a membrane. How to copy a molecule that codes for the next generation. The earliest life used the chemistry of hydrothermal vents and the chemistry of early photosynthesis to power the first metabolism. Some lived around the warm mineralized fluids of submarine vents. Some lived in shallow microbial mats in sunlit warm pools. Some used sulfur instead of oxygen as their electron acceptor. None of them looked like anything we would recognize as life today. They were single cells, smaller than a human red blood cell, slow growing in the languages of biology, but already running the basic chemistry that all later life would inherit. A sixth feature deserves attention as well: even though it concerns a kind of life that would not arrive for more than 1 billion years after this date. The most important biological development in the history of Earth, after the origin of life itself, was the rise of oxygen-producing photosynthesis. The cyanobacteria, the first organisms to split water using sunlight and release oxygen as a byproduct, would emerge sometime after 3.8 billion years ago, perhaps within the next several hundred million years. Their slow flooding of the atmosphere with oxygen would eventually transform Earth's surface, oxidizing the dissolved iron in the oceans, building the ozone layer in the upper atmosphere, and eventually permitting the rise of more complex life. None of this had happened yet, at 3.8 billion years ago. The Earth we are visiting was on the threshold of one of the longest, slowest, most consequential chemical transformations in the planet's history. The single cells that were doing it had not yet begun. Part 7. The Earth and its close moon. The Moon, at 3.8 billion years ago, was one of the most thoroughly studied bodies of the early solar system, both because of its proximity to Earth and because almost half of the lunar surface that we have ever brought to Earth has been dated by careful laboratory analysis. The samples returned by missions to the Moon, especially those taken from the rims of the largest basins, have given us our clearest direct dates for the Late Bombardment. By 3.8 billion years ago, the Moon was already an old body in the geological sense, but recently scarred in its largest features. Its original differentiation, the separation of a metallic core, a silicate mantle, and a low-density anorthositic crust, had occurred in the first 100 million years after formation. The bright lunar highlands we see today, those pale white regions covering most of the lunar surface, are made of that early anorthositic crust. They were already in place. They had been struck many times. They were saturated with craters. What was happening at 3.8 billion years ago, distinctively, was the Maria. The dark patches we see when we look up at a full moon are the lava-filled floors of the largest impact basins. Imbrium, Serenitatis, Chrysium, Nectaris, all of these were either freshly excavated at this date or had been excavated in the bombardment era and were beginning to fill with basaltic lava. The largest basins, struck during the late bombardment, had punched through the Moon's crust deeply enough to allow magma from the mantle to seep up over the next several 100 million years. The Maria flooding continued from about 3.8 billion years ago to about 3 billion years ago, gradually painting the dark patches that we recognize as the Moon's face today. The Moon was substantially closer to Earth at 3.8 billion years ago than it is today. Tidal friction in Earth's oceans transfers angular momentum from Earth's rotation to the Moon's orbit, slowing Earth's spin and pushing the Moon outward. The Moon currently recedes from Earth at a steady rate of about 3.8 centimeters per year. Run that recession backward across 3.8 billion years, and the Moon at this date was perhaps a quarter to a third closer than today. The exact figure depends on assumptions about how tidal dissipation varies with the geometry of the continents, but a reduction of 100,000 kilometers or more is a reasonable estimate. The Moon's apparent size in the sky at this date was correspondingly larger. The full Moon would have been a brighter, broader disk than the one we know. The features visible to the naked eye would have been the same Maria and highlands, although the Maria were less filled in at this date. The tidal pull on Earth's oceans was much stronger. Tides may have risen and fallen by tens or hundreds of meters along the most exposed coastlines. The tidal currents would have been correspondingly intense. The slowing of Earth's rotation produced shorter days. Estimates from a variety of methods, including tidal rhythmites preserved in ancient sedimentary rocks, place the early Earth's day length somewhere between 6 and 10 hours at 3.8 billion years ago. With shorter days came shorter nights, and the Sun and Moon would both have moved more rapidly across the sky than they do today. Sunrise and sunset were swift. Twilight was brief. The diurnal cycle, the daily rhythm of light and dark that almost every Earth organism has since evolved to track, was running at a much faster tempo. The lunar surface in this period was also being struck by the same late impactors that scarred Mercury, Earth, and Mars. The Moon, with its airless surface and its small mass, preserves every strike. The bombardment record on the Moon is the cleanest and most directly readable bombardment record we have. From it, we infer the timing of the storm on the other inner worlds, where weather and tectonics and biology have erased most of the evidence. For an observer standing on Earth at 3.8 billion years ago and looking up at the Moon at night, the Moon would have been a far more dramatic presence than tonight's Moon is for us. Larger, brighter, with the Maria less filled in, with the crater rims more sharply defined. The tidal pull of that closer Moon would have been felt in the very ground underfoot, since the same tidal forces that flex the ocean also flex the solid crust. The Moon and the Earth at 3.8 billion years ago were closer partners than they have been at any time since. They have been drawing slowly apart ever since. That slow recession continues. In the deep future, billions of years from now, the Moon will be much farther away than it is today. Eventually, in a future too far away to matter to any timescale we care about, the Moon may recede until it can no longer raise meaningful tides, and the Earth's rotation will lock to the Moon's orbit, the way one face of the Moon already locks to Earth's. But that is far ahead. At 3.8 billion years ago, the Moon was at one of the early points in its long outward drift, and it hung close, and it hung bright, and it filled the night sky in a way no later Earth observer would ever quite see again. Part 8. Mars, the wet world about to dry. Mars at 3.8 billion years ago is, in some ways, the most poignant transformation in this whole tour. The dry, cold, red world we see now was, at this date, almost certainly wet. It had a thicker atmosphere, running rivers, possibly a true northern ocean, lakes, snow on its high places, and very likely a global magnetic field. It had every architectural condition Earth had. But it was smaller, and that smallness sealed its fate. The era of Mars at this date is called the Late Noachian. It is the wet era of Mars history, the era when most of the surface features that record liquid water were being carved. Rovers and orbiters have catalogued an enormous body of evidence for surface water from this time. Dendritic valley networks, that is, river systems with branching tributaries like those carved by rainfall and snowmelt on Earth, run across the southern highlands of Mars. Lake beds, with layered sediments and clay minerals, are preserved at the bottoms of impact craters. Deltas, those fan-shaped sedimentary structures that build where rivers enter standing water, are visible at the edges of ancient lake basins. Mineral assemblages, including phyllosilicates and sulfates, require liquid water for tens of thousands to millions of years to form and are widespread on the surface of late Noachian Mars. The northern lowlands of Mars may have held a true ocean. The so-called Borealis ocean hypothesis suggests that a body of water covered perhaps a third of the planet's surface, with possible shoreline remnants still visible today, as old elevation contours running around the boundary between the lower northern terrain and the higher southern terrain. Whether the Borealis Ocean was a single permanent body or a series of intermittent shallow seas is contested. What is clearer is that, on the late Noachian Mars, there was a great deal of water at the surface, more than at any later time in the planet's history. The atmosphere at 3.8 billion years ago was much thicker than today's. Modern Mars has a surface atmospheric pressure of less than 1% of Earth's at sea level. Late Noachian Mars almost certainly had something substantially more, perhaps as much as a few percent of Earth's surface pressure or more, with the bulk of it being carbon dioxide plus water vapor, nitrogen, and trace gases. Surface temperatures across much of the planet may have averaged just below freezing, with seasonally warm areas allowing standing surface water. The climate, in the most recent models, was probably not Earth-like in detail. It was probably colder on average than the wet appearance of the valley networks suggests, with the rivers carved during transient warm episodes driven by volcanic eruptions, large impacts, or orbital cycles that shifted the planet's tilt and brought ice from high latitudes down to lower ones. Snowmelt, rather than steady rainfall, may have been the dominant source of the river flow. Either way, the world we are visiting was not a dry world. It was a world where water moved. Volcanism was vigorous. The Tharsis volcanic province was already building. Tharsis is the largest single volcanic feature in the solar system, a high plateau covering perhaps a fifth of the planet's surface, topped by several of the largest volcanoes ever observed on any world. Olympus Mons, the most famous, was either growing or had recently completed its main growth phase. Olympus Mons today stands about 22 kilometers above the Martian surface, more than twice the height of Mount Everest above sea level, and spans a base wider than several of Earth's countries. At 3.8 billion years ago, it was either reaching that height or close to it. Tharsis is so massive that the weight of its volcanic plateau warped the planet's crust globally. The northern-southern hemispheric dichotomy, the southern highlands of older cratered terrain versus the northern lowlands of younger, smoother terrain, was already established. Whether the dichotomy was caused by a giant northern impact, by mantle convection asymmetries, or by some other process, is still debated. Mars at 3.8 billion years ago may still have had a global magnetic field, or its global field may have just shut down. The evidence is preserved in magnetized crustal rocks of the southern highlands. Old volcanic rock that cooled in the presence of a global field retains a magnetic imprint, and the magnetized terrain of southern Mars records the existence of an ancient global field that died sometime around 4 billion years ago, give or take. The death of that field is what doomed Mars. With no magnetic shield, the solar wind began stripping Mars's atmosphere into space. The thinner the atmosphere grew, the less greenhouse warming it could provide. The colder it grew, the more water froze into the regolith. By about 3 billion years ago, much of the surface water was gone or sequestered underground. By 2 billion years ago, the planet was well on its way to becoming today's cold, dry world. Modern Mars retains some water as ice in its polar caps, as subsurface ice in vast permafrost layers, and possibly as briny liquid in very deep aquifers, but its surface today is essentially dry. The difference between Mars and Earth at 3.8 billion years ago is not chemistry. It is size. Mars is about 1/10 the mass of Earth and roughly half the radius. Its interior cooled faster. Its dynamo died younger. Its magnetic field was lost earlier. Without a field, the solar wind ate its atmosphere. Without an atmosphere, its surface temperatures collapsed. Earth's larger interior kept its dynamo going, kept its field strong, kept its atmosphere, kept its oceans. Mars, at 3.8 billion years ago, was on the edge of the long fall. Earth, at 3.8 billion years ago, was on the edge of the longer climb. For an observer standing on Mars at this date, perhaps in a Noachian valley network, a quiet stream running between low rocks, snow on the upland slopes, the pale young sun glinting through a thicker pinkish atmosphere. The water carries fine red sediment downstream into a lake. The lake's bottom is layered with clay and sulfate minerals that will, in 3.5 billion years' time, be photographed by a rover whose creators have not yet evolved. A few additional features of Mars at 3.8 billion years ago deserve mention. The first is the question of life. The same conditions that made early Mars wet also made it potentially habitable by simple microbial life of the same general kind that was beginning to take hold on Earth at this date. The early Mars surface had liquid water, energy sources from volcanism and from sunlight, and the basic chemical inventory required by biochemistry. Whether biology actually took hold on Mars during the wet era is one of the great open questions of astrobiology. Sample return missions, returning rock samples from carefully chosen locations on Mars to laboratories on Earth, may someday provide a tentative answer. The samples currently being collected by rovers on Mars have been chosen specifically with this question in mind. If life did establish itself on early Mars, it may have left behind biological signatures in the same lakebed sediments that record the water, signatures that will only become visible under careful study in terrestrial laboratories. The second feature is the panspermia possibility. Because Mars at 3.8 billion years ago was warmer, wetter, and possibly habitable earlier than Earth was, some researchers have suggested that life may have originated on early Mars and been transferred to Earth by meteoritic exchange. Material from Mars is routinely flung into space by large impacts on the Martian surface, with some of that material eventually reaching Earth. We have meteorites on Earth today that we have identified as Martian in origin. If early Martian life had been carried in such meteorites, it could have arrived on Earth and contributed to terrestrial biogenesis. This is the panspermia hypothesis in its simplest form. It is currently neither confirmed nor refuted, but it is taken seriously enough as a possibility that the wet era of Mars is treated with particular interest by astrobiologists. The third feature is the difference between the highlands and the lowlands. The southern highlands of Mars, which preserve the cratering record of the bombardment, are ancient, heavily cratered terrain. The northern lowlands are smoother, younger, and lower in elevation, and they are the candidate location for the Borealis Ocean. The dichotomy between the two terrains is one of the most pronounced features of any planet's surface in the solar system. Whatever process produced it, it was clearly established by 3.8 billion years ago, and probably much earlier. The contrast between the two halves of Mars is one of the most distinctive marks of the planet's early history. The fourth feature is the role of impacts in delivering water to Mars. Like Venus and Earth, Mars received a significant fraction of its surface water from the icy and carbonaceous bodies that struck it during and after the bombardment. The water inventory of early Mars was, in part, a gift from the same storm of impacts that scarred its surface. The same impactors that gouged out the great impact basins of the southern highlands also added water, carbon, and other volatiles to the planet's surface. The contradiction between the destructiveness of the bombardment and the constructiveness of the bombardment is one of the recurring themes of early solar system history. The fifth feature, finally, is the slow loss that was about to begin. The atmospheric escape that would eventually carry away most of Mars's surface water and most of its early atmosphere was just starting to dominate at 3.8 billion years ago. The death of the magnetic field, whenever it happened precisely, exposed the upper atmosphere to the full force of the solar wind. The Sun was more active in this era than it is today, with stronger solar winds and stronger flaring. The loss rate was higher per year than it is now. The cumulative loss over the next 2 to 3 billion years would gradually thin the atmosphere from something like a fraction of Earth's surface pressure to something like 1% of it. The wet Mars of 3.8 billion years ago, in other words, was on the threshold of a long drying that would carry across nearly all of geological time. Part 9. Jupiter and its family. Returning to the outer solar system, Jupiter, at 3.8 billion years ago, is the heaviest single object in the system after the Sun, more massive than all of the other planets combined. Its enormous mass and its gravitational reach have, by this date, finished shaping the architecture of the inner solar system in two important ways. First, it has cleared a region around its own orbit, sweeping up or scattering most of the small bodies that would otherwise compete for its space. Second, by its participation in the Nice model rearrangement, it has driven the late storm of impacts that has just ended. The interior of Jupiter at this date follows the structure we still describe today. At the outermost layer, an envelope of molecular hydrogen mixed with helium and trace amounts of heavier gases, extending downward for thousands of kilometers under increasing pressure and temperature. Below that, the metallic hydrogen mantle, where pressures are so extreme that hydrogen atoms lose their electrons to a sea of conduction, behaving like a molten metal. Below that, the small, fuzzy core, perhaps not as sharply defined as a clean, rocky kernel, perhaps blended into the surrounding metallic hydrogen as a gradient of heavier elements. This interior structure generates the strongest planetary magnetic field in the solar system, a vast magnetosphere that, if it could be seen from Earth, would appear several times wider than the full moon in the sky. The atmospheric appearance at 3.8 billion years ago is the same banded pattern of zones and belts we recognize tonight. The zones are bright, cool, ammonia-rich high clouds. The belts are darker, warmer, lower clouds where the deeper atmosphere shows through. The colors arise from chemical species mixed into the cloud layers, ammonium hydrosulfide, and various photochemical products that we still do not fully understand. The exact chemistry of the visible cloud tops at this date might have been slightly different, since the early solar system chemistry of the cloud-forming layers depended on the inventory of trace species, but the basic banded appearance would have been the same. The Galilean moons of Jupiter at 3.8 billion years ago were already in their orbits, already differentiated, already on their long lives. Io, innermost, was already volcanic. Tidal heating from its orbital coupling to Europa and Ganymede flexed its interior continuously, driving the constant volcanism that gives Io its yellow and orange and red modern surface. At 3.8 billion years ago, the volcanism may have been even more vigorous than today, since the orbital coupling that drives it was likely stronger in the past. Io's surface, then as now, was constantly being repaved by sulfur and silicate eruptions. Europa was already an ocean world. Beneath an icy crust, a global ocean of liquid water, kept liquid by tidal flexing in its orbital coupling to Io and Ganymede. The depth of that ocean at 3.8 billion years ago is uncertain, and the icy crust above it may have been thicker, since the sun was dimmer and the surface was colder. But the ocean was almost certainly there. Europa is one of the longest-running water worlds in the solar system, and the ocean has likely been continuous for almost the planet's whole history. Ganymede, the largest moon in the solar system, at 3.8 billion years ago, was a world larger than the planet Mercury, with its own complete differentiation, an iron-rich core, a rocky mantle, and an icy outer crust, with possibly a subsurface ocean. Ganymede, uniquely among the moons, has its own intrinsic magnetic field, generated by a dynamo in its iron core. Whether that dynamo was already running at 3.8 billion years ago is uncertain, but the interior conditions to support it were in place. Callisto, the outermost of the Galilean Four, was at 3.8 billion years ago a heavily cratered ice and rock world without the strong tidal heating of the inner three. Its surface preserves the cratering record back to the bombardment era. By this date, much of that cratering record was already laid down, and Callisto's surface looked like a darker, smaller version of what we see today. Beyond the Galilean moons, Jupiter at 3.8 billion years ago had a much smaller retinue of irregular outer moons than it has now. Many of the small captured bodies that orbit Jupiter today were not yet bound to the planet at this date. They drift through the outer solar system for hundreds of millions of years, occasionally approaching Jupiter close enough to be captured into its enormous gravitational well. The Jupiter system of 3.8 billion years ago is a tidier system than today's. 4 big inner moons in well-ordered orbits, a few smaller inner companions, and much of the local space still empty. The Jovian magnetosphere at this date was, like the planet itself, slightly more vigorous than today. Younger stars rotate faster and have stronger magnetic fields, and the same is broadly true of younger gas giants. Jupiter's magnetic field at 3.8 billion years ago was, plausibly, somewhat stronger than today's. The magnetosphere bombarded the surface of Io with energetic particles, sputtering material off the moon and feeding a torus of ions along Io's orbit, the way it still does today. If we were watching Jupiter from a vantage in the outer solar system at this date, the planet would have looked almost exactly the way it looks through a good amateur telescope tonight. The same striped banding, the same slow rotation, one Jovian day in about 10 hours. The same shadow play of the Galilean moons crossing the disk. The Great Red Spot, which is the one feature that might or might not have been present, would have to be acknowledged as a question rather than an observation. But the larger pattern of the planet, its enormous quiet presence among the outer worlds, would have been entirely recognizable. There is one further detail about Jupiter at this date that is worth noting in passing. The slow gravitational interaction between Jupiter and the inner solar system has, across geological time, continued to influence the small bodies of the asteroid belt. The Kirkwood gaps, the distinctive empty zones in the asteroid belt at certain orbital periods that resonate with Jupiter, were being established and stabilized at 3.8 billion years ago. Jupiter's gravity removed bodies from those resonant orbits efficiently, sweeping the belt clear at certain distances. The structure of the modern asteroid belt, with its distinctive gaps and concentrations, was being set by Jupiter at this date. The planet was finishing the work it had begun during the bombardment, sculpting the small body population of its inner neighborhood by patient gravitational influence. The Jovian system at 3.8 billion years ago was also a busy chemical environment. The interaction of the magnetosphere with the surfaces of the Galilean moons, the constant rain of energetic particles on Europa's icy crust, the slow sputtering of material from Io and Europa and Ganymede and Callisto, the chemical processing of that material into the various ions and atoms that filled the magnetosphere, all of this was already running. The system was not a quiet one despite Jupiter's slow rotation against the dark. It was active, layered, electrically vigorous. The same chemistry that we map today, the sulfur and oxygen and sodium and other species detected in Jupiter's vast magnetic environment, was already being produced and circulated. The Jupiter system has been one of the most chemically active places in the solar system for almost the planet's entire life. Part 10. Saturn, Uranus, Neptune. Beyond Jupiter, the 3 more distant giants were each living their own version of the same long, quiet middle age that Jupiter was settling into. Each had its own distinctive structure, its own atmospheric chemistry, its own retinue of moons. Each was almost identical to its modern self, with one or two important differences. Saturn, at 3.8 billion years ago, turned slowly on its tilted axis, banded in the same pale gold and cream of cloud tops, shaped by zones and belts. Its hydrogen and helium structure, its internal layers, its deep convection, its slow rotation producing ablateness at the poles, all of this was the same. The hexagonal jet at the North Pole was already turning, since the hexagon is a stable feature of the planet's atmospheric dynamics that requires only continuous rotation and the right vertical wind shear to produce. Saturn's appearance to the eye was nearly identical to today's. The main visible difference, as we discussed earlier in this tour, was the absence or near absence of the modern ring system. The bright rings of Saturn, which give the planet its iconic look, are too young to have been in place at 3.8 billion years ago, based on multiple independent lines of evidence. So the Saturn of this date was a paler world without its great ring crown, attended only by its system of moons. Triton, the largest Saturnian moon, was already in its orbit, with a thick nitrogen atmosphere and slow circulation of methane through the troposphere. Triton at 3.8 billion years ago is one of the most interesting moons to consider because some of its features may have been more vigorous in the past than they are today. Methane is continuously broken apart by sunlight in Triton's upper atmosphere, with the products either reacting to form complex organic chemistry or escaping to space. Without continuous resupply, Triton's atmospheric methane should have been depleted long ago. The resupply must come from some interior source, possibly cryovolcanism, possibly methane storage in clathrate cages in the moon's icy crust. At 3.8 billion years ago, the resupply may have been more vigorous, with a thicker atmosphere and possibly more frequent cryovolcanic activity, producing the methane lakes and rivers we know exist on Triton today. Enceladus, much smaller than Triton, orbits Saturn at a closer distance. Tidal flexing from its orbital coupling to Dione warms its interior, driving the south polar plumes that we have observed in modern times. At 3.8 billion years ago, the tidal heating arrangement may have been somewhat different, since the orbital architecture of the Saturnian system has evolved over geological time. Whether Enceladus had a stable global subsurface ocean at this date is uncertain. The geological record of Enceladus is preserved on its surface, but only in the very young features of recent activity. We can infer that the interior was warming. Whether it had broken through to a stable internal ocean is open. Other Saturnian moons existed at this date, including Mimas, Tethys, Dione, Rhea, and Iapetus. They were each in their orbits, each broadly the same body we observe today. The cratered surfaces of these moons preserve the record of the late bombardment, since the same scattered planetesimals that struck the inner solar system also struck the Saturnian system. Uranus, the first of the ice giants, was at 3.8 billion years ago already tipped on its side. The catastrophic giant impact that tilted Uranus's rotation axis nearly perpendicular to the ecliptic occurred in the planet's first 100 million years, long before this date. By 3.8 billion years ago, Uranus had been spinning sideways for a very long time. Its interior, a thick mantle of supercritical water, methane, and ammonia under high pressure around a small rocky core, was already established. Its atmospheric appearance, the same pale blue-green that we see today, was already in place. What may have been different about Uranus at this date is its internal heat. Modern Uranus radiates strikingly little heat from its interior, far less than Neptune, even though the two planets are almost identical in mass and composition. The leading explanation is that the same giant impact that tipped the planet also disrupted whatever convective heat transport regime Uranus would otherwise have inherited, leaving the deep interior unable to dump its formation heat efficiently. At 3.8 billion years ago, that long, slow heat trapping was still in its early stages, and Uranus may have been a noticeably brighter source of infrared emission than it is now. Its visible appearance, the same blue-green of methane-tinted cloud tops, would have looked the same. The 5 major Uranian moons, Miranda, Ariel, Umbriel, Titania, and Oberon, were already in place. They formed from a circumplanetary disk after the tilting impact, in a series of orbits that lie close to the planet's tilted equatorial plane. The thin ring system of modern Uranus may be younger than this date, possibly formed by the disruption of a small moon at some later time. Neptune, at 3.8 billion years ago, is structurally identical to Uranus, the same ice giant mantle of supercritical water, methane, and ammonia around a rocky core. Its atmospheric appearance is the same deep blue that we see today, colored by methane absorption. Its supersonic equatorial winds, the strongest sustained winds on any planet in the solar system, were probably already underway. Its great dark spots, those transient anticyclonic storms that form and fade across decades, were almost certainly forming and fading at this date as well. What Neptune did not yet have was Triton. Today, Triton is the largest moon of Neptune and the 7th largest in the solar system. It is also one of the strangest, orbiting Neptune in the retrograde direction, opposite the planet's rotation, on an orbit highly inclined to Neptune's equator. The retrograde orbit, the high inclination, and the compositional similarity to Pluto all point to a capture origin. Triton began life as a Kuiper belt body and was later snared by Neptune's gravity. The exact timing of the capture is uncertain, but it appears to have happened after the bombardment era, possibly hundreds of millions of years after 3.8 billion years ago. At this date, Neptune's moon system was lighter and more orbitally regular than it is today, populated by smaller bodies. Some of those small original moons may have been disrupted later by tidal interactions with Triton when Triton arrived, with their remains possibly contributing to the modern Neptune ring system. The story of Triton's eventual capture is one of the more dramatic events in the post-bombardment outer solar system. The capture probably involved a binary pair of Kuiper belt objects passing close enough to Neptune that the gravitational interaction broke the pair apart, with one of the two thrown free, and the other slowed enough to remain bound to Neptune. The captured body was Triton. The slowing process left Triton on a retrograde, highly inclined orbit. Tidal friction with Neptune then circularized the orbit over hundreds of millions of years, bringing Triton to its current, nearly circular path around the planet. The tidal heating released during that circularization may have melted Triton's interior, producing the smooth, differentiated body we see today, with its tenuous atmosphere of nitrogen and methane, and its strange south polar cryovolcanic plumes. All of this lay ahead at 3.8 billion years ago. There is a small additional detail about Neptune at this date worth noting. The planet's internal heat is one of its more striking features. Neptune today radiates about 2.6 times the solar energy it receives, compared with about 1.7 times for Jupiter, slightly less than 1 for Uranus, and about 2 for Saturn. The high internal heat of Neptune is one of the puzzles of the outer solar system. The leading explanation is that Neptune retains its formation heat efficiently because of its interior structure, with the supercritical fluid mantle convecting freely and carrying heat outward to the cloud tops. At 3.8 billion years ago, with somewhat more formation heat still to release, the internal contribution to Neptune's luminosity was probably even stronger. Neptune may have been a slightly brighter infrared source then than it is now, though the difference would have been small. Saturn at this date offers a similar story of slowly cooling internal heat. The helium rain that contributes to Saturn's interior structure is itself a heat source. In the deep envelope, helium becomes immiscible with hydrogen at certain pressure-temperature combinations, and droplets of pure helium fall through the hydrogen, releasing gravitational potential energy that is converted to heat as the droplets descend. The helium rain has been running for most of Saturn's life. At 3.8 billion years ago, it was running at approximately its current rate, contributing its modest excess heat to the planet's energy budget. The Saturn we are visiting was not noticeably hotter than today's Saturn. It was simply the same planet, with the same slow internal processes running their long, quiet course. Part 11. The small bodies and the outer dark. Between and beyond the planets, the population of small bodies that fills the solar system was in dramatic transition at 3.8 billion years ago. The bombardment had not only struck the inner worlds, it had reshaped the entire small body population of the solar system. The asteroid belt, which lies between the orbits of Mars and Jupiter, had recently been depopulated by the same Nice model orbital rearrangement that produced the bombardment. The early asteroid belt, before the rearrangement, was much more massive than the modern belt, possibly containing several Earth masses of material in total. The crossing of the Jupiter-Saturn resonance during the rearrangement pumped up the eccentricities of the small bodies in the belt and scattered most of them. Some struck the inner worlds. Some were ejected into interstellar space. Some were absorbed by Jupiter. Some remained, settling into the much more stable but much sparser modern belt, with a total mass, perhaps 1,000th of Earth's mass, distributed across hundreds of thousands of small bodies. By 3.8 billion years ago, the asteroid belt was thinning into something approaching its modern, sparse form. The largest asteroids of today, Ceres and Vesta, and Pallas and Hygeia, were already in place, having survived the rearrangement. Ceres, the largest body in the belt and the smallest of the recognized dwarf planets, was already differentiated, with a layered interior of rock and ice. Vesta was already a dry, basaltic body, the result of early melting and volcanism that gave it its modern surface. The smaller asteroids in the belt were in various states, some intact survivors from the early disk, some fragments of larger bodies that had been broken apart by collisions. Beyond Jupiter, the Kuiper belt was being raked outward by the migration of Neptune. The original outer disk of icy planetesimals, which had extended from somewhere around Neptune's original orbit outward, was being scattered. Some bodies were thrown inward toward the giant planets, contributing to the bombardment. Some were ejected to interstellar space. Some were pushed outward into more distant orbits, becoming the population of the modern Kuiper belt and the modern scattered disk. Many were thrown to such great distances that they entered the Oort cloud, the spherical shell of long-period comets that surrounds the entire solar system at distances of thousands to 100,000 astronomical units. Pluto and the other large dwarf planets of the Kuiper belt were settling into their modern orbits at 3.8 billion years ago. Pluto's orbit, which crosses Neptune's, is stabilized against close approaches by a 3:2 resonance with Neptune, the same kind of resonance that locks many other Plutinos into step with that planet. The resonance was established during Neptune's outward migration. By 3.8 billion years ago, Pluto and the major Plutinos were largely in their final resonant orbits. The Oort cloud was in a sense a souvenir of the bombardment. It preserves, frozen, the bodies that were not absorbed in the storm. By 3.8 billion years ago, the Oort cloud was largely populated, holding the icy bodies that had been flung outward by gravitational interactions with the giant planets. The Oort cloud contains an estimated 1 trillion or more icy bodies distributed over a vast spherical volume that extends roughly halfway to the nearest stars. The cloud is so distant and so sparsely populated that it has never been directly observed. We know it exists because of the long-period comets that occasionally fall from it into the inner solar system, arriving on highly elongated orbits with random orientations to the plane of the planets. The spherical symmetry of those incoming orbits is the cloud's signature. The interstellar medium that surrounded the early solar system was, at this date, similar to what surrounds us tonight. The Sun is moving through the local interstellar medium at about 85,000 kilometers per hour. The motion through that medium produces a heliosphere, a bubble of solar wind that holds back the cosmic rays and the interstellar gas. The heliosphere was already in place at 3.8 billion years ago, Chash, although its size and shape would have varied with the Sun's activity, which was somewhat higher then than now. 3 to 4 light-years away from the Sun, the nearest stars in the local stellar neighborhood were not the same stars we see today as our nearest neighbors. The Alpha Centauri system, our current nearest neighbor, lies at 4.2 light-years today, but the stars in the solar neighborhood drift past each other on long timescales. The Sun's nearest stellar neighbors 3.8 billion years ago were different stars, and the Alpha Centauri system had not yet drifted into its current proximity. The night sky over early Earth, while broadly similar in its overall structure, had a slightly different set of near neighbors, although none of them would have looked dramatically different to the eye at the great distances involved. In the outer dark, beyond the Oort cloud, the rest of the galaxy was almost exactly the galaxy we know. The disk of stars and gas and dust was already in place, with the same general structure of spiral arms, the same central bulge, the same dark matter halo surrounding it all. The galaxy had been turning for billions of years before our solar system had even formed. From its perspective, our entire local system was a small new feature in a much larger old structure. There are some further features of the small body population at 3.8 billion years ago worth attending to. The first is the role of comets in the inner solar system. The same Oort cloud and the same scattered disk that were being filled with icy bodies at this date have continued, ever since, to occasionally fling comets back into the inner solar system. A comet from the Oort cloud, perturbed by a passing star or by the galactic tide, may begin a long inward journey that takes it from a distance of 50,000 astronomical units to a close pass by the Sun. The journey takes hundreds of thousands of years. When the comet finally reaches the inner solar system, its surface ices begin to sublimate under the increased sunlight, producing the coma and the tail that make comets visible from Earth. Many of the comets we observe today are bodies that were placed into the Oort cloud during or shortly after the bombardment era and have been waiting in the cold and the dark for billions of years before falling back inward. The second feature is the centaurs. Beyond Jupiter, but inside the orbit of Neptune, there is a population of small icy bodies on unstable orbits, drifting between the orbits of the giants under the gravitational influences of each. These bodies are called centaurs, after the mythological creatures that combine two forms, because they are intermediate between the asteroids of the inner solar system and the comets of the outer solar system. The centaur population has been replenished across geological time by Kuiper belt objects, scattered inward by Neptune. At 3.8 billion years ago, the centaur population was being heavily fed by the ongoing scattering, with many bodies on temporary orbits among the giants. The third feature is the trans-Neptunian region. Beyond Neptune, the modern Kuiper belt extends from about 30 astronomical units to about 50, with a sharp drop in population beyond that distance. The structure of the modern belt including the presence of resonant populations like the Plutinos and the so-called classical Kuiper belt of objects on stable, nearly circular orbits, was being set by Neptune's outward migration. By 3.8 billion years ago, much of this structure was in its final form. The bodies in stable resonant orbits would remain there for the rest of the solar system's life. The bodies in unstable orbits were being scattered, ejected, or accreted by the giant planets. The fourth feature is the so-called scattered disk, the population of icy bodies on highly eccentric orbits that take them far out beyond the main Kuiper belt. The scattered disk objects, including the largest known, were placed into their current orbits during the same scattering events that filled the Oort cloud. At 3.8 billion years ago, the scattered disk was being populated by the most recent scattering events, with bodies on orbits that took them many hundreds of astronomical units from the Sun. The fifth feature is interstellar space itself. Although the focus of our tour has been on the solar system, we cannot completely ignore the surrounding interstellar context. The Sun, at 3.8 billion years ago, was orbiting the center of the galaxy on roughly the same path it follows today, completing one orbit every 200 million years or so. Across the past 3.8 billion years, the Sun has completed nearly 20 orbits around the galactic center. The local stellar neighborhood has changed across each orbit, with the Sun passing through different regions of the galactic disk, encountering different gas clouds, drifting past different sets of nearby stars. The nearest neighbors of the Sun at this date were a different set of stars from those nearby today. Some of the gas clouds the Sun has drifted through across geological time may have been dense enough to compress the heliosphere significantly, with possible consequences for the cosmic ray flux reaching the inner solar system. Whether the Sun was drifting through any particular cloud at 3.8 billion years ago is uncertain, but the broader picture of a Sun moving through a changing galactic environment across long timescales was as true then as it is now. Part 12. The Young Sun. We come, finally, to the Sun. Across the entire tour of 3.8 billion years ago, the Sun has been the dim, slightly younger version of the star we know. About 70% of its current luminosity. The same yellow main sequence star, the same spectral class G2V, just at an earlier stage in its long, slow main sequence brightening. The early Sun had completed its first dramatic phase by 3.8 billion years ago. The T Tauri phase, the violent youth of a sun-like star, lasts only the first few tens of millions of years. During that phase, the star has not yet stabilized its hydrogen fusion. It is contracting, heating, occasionally flaring with enormous outbursts that shower its surroundings with high-energy radiation. The T Tauri phase ends when the star settles onto the main sequence. For the Sun, that settlement happened well before 3.8 billion years ago. By this date, the Sun was in its long, calm middle age. The faint young Sun condition is the most important fact about the Sun at this date. The Sun has been brightening, gradually, ever since the start of its main sequence life. The brightening is driven by the slow change in the composition of the core, as hydrogen is converted to helium, and the core becomes denser and hotter and more efficient at fusing. The luminosity rises slowly, by perhaps a few percent per billion years. 3.8 billion years ago, the Sun was about 70% of its current luminosity. 3.5 billion years ago, perhaps 75%. 2 billion years ago, perhaps 85%. The brightening will continue. In about a billion years from now, the Sun will have brightened enough to begin destabilizing Earth's climate, regardless of any other factor. The Sun's color at 3.8 billion years ago was very nearly the same yellow as today. A G-class star changes color only modestly across its main sequence life. The visible spectrum, the colors we recognize, would have looked nearly identical to a human eye. The light was just dimmer. The sun rotated faster 3.8 billion years ago than it does now. Young stars spin faster. They lose angular momentum slowly across their lives through the magnetic coupling between their stellar winds and their magnetic fields. The sun has been gradually slowing down across its main sequence life, just as it has been gradually brightening. At 3.8 billion years ago, the sun's rotation period at the equator may have been about 20 days, compared with 25 days today. The sun's magnetic field, sunspots, flaring, coronal mass ejections, and overall solar activity were stronger then than today. Solar flares were probably larger on average. Coronal mass ejections were probably more frequent. The total solar wind was stronger, perhaps 3 or 4 times the modern mass loss rate. The sun's ultraviolet output was particularly enhanced, since the ultraviolet excess scales steeply with the level of magnetic activity. This higher ultraviolet flux contributed both to atmospheric escape from the inner rocky worlds and to the chemistry of their upper atmospheres. The increased solar wind, the higher flaring rate, and the stronger ultraviolet output mattered most for Mars and for early Venus. Mars, whose magnetic field was just dying at this date, would have been increasingly exposed to a more vigorous solar wind without a field to hold it back. Each large flare from the active young sun could strip more of Mars's atmosphere into space. Venus, with its possibly weaker field and its closer distance to the sun, also lost atmospheric water through ultraviolet photolysis at a higher rate than it does today. The sun's youth, in other words, was part of what made the early solar system habitable in places, and also part of what would later destroy that habitability on those places. Earth was largely protected from this enhanced solar activity by its strong magnetic field. The dynamo in Earth's molten iron outer core was already running vigorously, generating a global magnetic field strong enough to deflect most of the solar wind around the planet, rather than allowing it to strip the upper atmosphere. The auroras at 3.8 billion years ago would have been more vigorous than today's, fed by the higher solar wind flux, and they may have extended to lower latitudes during particularly large geomagnetic storms. But the basic protection was in place. Earth held its atmosphere. The interior of the Sun at this date was structurally similar to the interior of the Sun today. A central core of hydrogen fusion, surrounded by a radiative zone in which energy is transported outward by photon diffusion, surrounded by a convective zone in which energy is transported outward by hot rising gas and cool descending gas, surrounded by the visible photosphere where the photons finally escape into space. Above the photosphere, the chromosphere, and the corona, with the corona heated to temperatures of millions of degrees by mechanisms that even today we do not entirely understand. The same coronal heating problem that puzzles modern solar physicists was already in play at 3.8 billion years ago. The Sun has been carrying that mystery, quietly, across its entire main sequence life. The Sun has been on the main sequence for about 4.6 billion years, and will remain on the main sequence for another 5 billion years or so. 3.8 billion years ago marked one early waypoint along that long, stable middle age. The Sun has been the slow, steady background to everything else we have visited tonight. Brighter now than then, but still the same star, still turning at the center of the same solar system, still holding its 8 planets and their families of moons in their patient orbits. Part 13.3 Worlds with Water. We have walked through the solar system now at 3.8 billion years ago. The gas giants, almost identical to their modern selves, settled and quiet. Mercury, scarred and contracting under a strong young sun. Venus, possibly oceanic, the great might-have-been of the inner solar system. Earth, warm and oxygen-poor and microbial, the cradle of what would later become a biosphere. The moon hung close and bright, raising tides that crossed continents. Mars, wet and weathered, on the edge of its long, slow drying. The small bodies of the outer disk recently reorganized, the Kuiper belt being raked outward, the Oort cloud filling with scattered comets. The sun, slightly dimmer, slightly faster spinning, slightly more active, but still the same yellow main sequence star we know. One of the most striking features of the solar system at this date is that habitability, as far as we can tell, was the rule rather than the exception among the rocky worlds. 3 worlds out of 4 may have held standing surface water at once. Venus had it, probably, and would lose it over the next 2 billion years. Earth had it, and would keep it. Mars had it, and would lose it over the next billion years. Only Mercury, too small and too close to the Sun, had no water to lose. This is not the configuration we see today. Today, only one rocky world in the solar system has surface water in any significant quantity, and that one world holds a complex biosphere built on it. The other rocky worlds are dry, or hidden, or both. The contrast between then and now is striking. The contrast carries one of the simplest but most important lessons of comparative planetology. Habitability is not a property of a planet alone. It is a property of a planet at a particular moment in its evolution, under a particular set of conditions, with a particular history of impacts and atmospheric escape, and dynamo activity and stellar input. 3.8 billion years ago, the inner solar system was at a moment when all 3 of its larger rocky worlds had the architectural conditions for surface water. The Sun was dim enough to allow Venus to hold water at its closer distance. The Sun was bright enough to allow Mars to hold water at its farther distance. Earth, in the middle, had it in abundance. Whether life took hold on any of those worlds, beyond the simple microbial life that we know was on Earth, is a question that current and future missions are still working to answer. If we were to compress the entire tour of tonight's video into a single image, it might be this: a solar system whose architecture is already set, whose worlds are still being decided. The giants finished. The rocky planets in transition. 3 worlds with water, 2 of which would lose it. A dim young sun shining over them all. A bombardment just ending. The first single-celled life beginning. The moon hung close, and the day on Earth running fast, and the air on Earth orange under that dim, soft light. We have looked back at almost 4 billion years ago. The pattern we have found is one of unfinished worlds, of worlds in transition, of conditions that were temporarily widely habitable and then later not. The pattern is not unique to our solar system. Every planetary system, around every star, goes through some version of this same early phase. Worlds form. Atmospheres establish or escape. Surface oceans appear and disappear. Some worlds keep their conditions for life across geological time. Others lose them. The question of how often the conditions hold long enough, on worlds with the right architecture, for biology to take hold and persist, is one of the great open questions of astronomy. Tonight, we have not tried to answer that question. We have only tried to walk slowly through a single solar system at a single moment in its long history. The walk has been gentle. The light has been dim. The faint young sun has shone, and the bombardment has tailed off, and the worlds have turned, and we have looked at each of them in turn, and we have asked what they were before they were what they are now. 3.8 billion years ago is a long time. It is so long that the worlds we have visited are barely recognizable from their modern selves, and yet still close enough to today that the solar system's architecture had already been set. It is a midpoint of sorts, a boundary between the chaotic early history and the long, quiet Middle Age. A moment when many things were still possible and many things were already done. We will not pass this way again. Each of the worlds has moved on. Each has become something more particular than it was. But the moment, in some sense, is still there in the deep history of every body in the solar system, recorded in the oldest rocks and the oldest craters and the oldest atmospheric signatures. The solar system we live in tonight is still partly the solar system of 3.8 billion years ago, in the same way that any person is still partly the person they once were. There is a final image, perhaps, that holds the whole tour together. If we could rise above the plane of the solar system at this date and look down, we would see something almost identical to what we would see looking down today. The same orbits, the same distances, the same general arrangement of bodies. But each individual body, looked at closely, would be a stranger to its modern self. The blue marbles and red dots and green pearls of the modern solar system, the worlds whose photographs we know, would all be slightly different. Earth would be more orange than blue, more covered in ocean, with no green continents. Mars would be wetter, with patches of standing water reflecting the dimmer sun. Venus would be paler, with cloud breaks revealing shallow water at the surface. The four giants would be almost the same, banded and quiet, with their families of moons running through patient, circular orbits. The whole picture would feel familiar and strange at the same time. Recognizable in its architecture, unrecognizable in its details. The solar system we live in tonight, in some deep sense, was already there. But it was being decided. And so we leave the solar system where we found it. 3.8 billion years ago, with a warmer Earth under its strange orange sky, a wetter Mars under its dimmer pale sun, and a quieter Venus that had not yet lost its oceans. The story of each world was still being written then. The story is still being written now. Let your breathing slow. Let the long arc of time soften around you. Sleep well and good night.